All right, let's get started. We are very happy to have Jize Yu from IIS. And Jize is going to talk about representation theory of quantum groups at roots of unity, starting with representations in positive characteristic for algebraic groups.
Okay, thank you very much for the introduction and inviting me to give these talks. And so today we will start by looking at rational representations in positive characteristic. So just a very quick introduction. So the goal of today's talk is to give a very quick review of some classical results in rational representation theory of algebraic groups in characteristic P. So the main topics today are as follows. So we discuss induction functors, and we discuss the dual vowel modules and the vowel modules. And we proceed to discuss the Steinberg's tensor product theorem, and followed by the Kemp's vanishing theorem. And finally, we finish the talk by talking about the linkage principle. Okay. The main references are Ewan's notes, which has the same name, the rational representations in positive characteristic, and also Youngson's book, representations of algebraic groups. And there's also lecture notes by Joshua Chiapera and Jordi, lectures on the geometry and modular representation theory of algebraic groups.
So maybe I should make a comment. Those notes which Jize is referring to were just, very brief review of some things in Yansing plus some mistakes of my own. So Yansing is actually preferable.
Yeah, and the notes are available online. Okay, let's quickly recall the notations we have seen in the previous lectures and also will be used in this talk. So again, P will be a prime number, and F is an algebraically closed field of a characteristic P, and G will be a connected reductive, connected algebraic group over F, and we denote its Lie algebra also by this G over F, and we will make some other assumptions about G later, but I will make this very clear. Okay, so we write rep G to be the category of all rational representations of G, and rep finite dimension G as the category of all the finite dimensional representations of G. And the lambda will denote the weight lattice of G, and the lambda plus will denote the dominant weights. And we choose Maximo Torres and a Borel subgroup of G, and we write W for the Vowel group of G, and U will be the unipotent radical of the Borel, and we write U minus for the opposite unipotent, and we write alpha 1, alpha 2 to alpha R for the simple roots of G, and alpha 0 will be the negative root such that alpha 0 check is minimal. And so by this assumption, alpha 1 to alpha R are actually the simple affine roots. And the W0 will denote the longest element in the Vowel group. And the rho is the half sum of all the positive roots. And this phi will denote the root system, and pi will be the set of simple roots.
By the way, when you say that alpha 1 through alpha R are simple affine roots, that's definitely right, but these are not all simple affine roots.
Right.
So you also need a root which corresponds to alpha 0.
Right.
Is G affine?
Sorry, G is a connected algebraic group over F. Yeah.
And it's affine.
Yeah, exactly. It's obviously. Yeah.
Well, not every algebraic group is affine, but we only care about affine groups.
Exactly. But on an elliptic curve, I mean, you do assume affine.
Right. Okay. So let's start looking at family. of rational representations. So we first look at weights. So the rough idea is representations of T over F are not different. Oops. From the representations of T over the complex number. Here's the lemma. So for any representation V of T, V is completely reducible. Oops, apologize for my writing. And irreducibles are precisely characters. Okay. So for any representation of G, we have a decomposition into weight spaces. V equals to a direct sum of V chi. So where V chi are those vectors in V such that T acts on it is by this character. So we note the Vowel group equals to the normalizer of T inside G quotient by T, then it's not hard to see that V chi is isomorphic to VW acts on chi for chi in lambda and element W in the Vowel group. Okay. So the next topic is the induction functor. Okay. So let's say we have H be an algebraic subgroup. Okay. And we have we have a natural restriction functor from G to H, which takes G modules to H modules. Oops. And the goal of this section is to find the right H-on functor of the restriction functor. Okay, so how to construct this functor? So for any representation of G, we look at this twisted product, G times N.
You mean representation of H?
Exactly, sorry. It's definitely, oops. It's definitely H. Right. Oops. Right. So the oops. Sorry, do I need to?
You're not sharing.
Yeah, I need to share again. Yes. Okay. All right. Sorry for the technical. This is the first time I'm giving a talk using iPad. So, right. So this is defined to be the quotient of G cross M by H. So where H acts on G cross M and T diagonal.
Well, G times M, and also this works when M is finite dimensional.
Yes. And right.
It acts on G times M, not G times H.
Did I write G times M?
You're right, G times H.
Oh no, I mean this H is a superscript of the times.
Line number 3. It's written G times
right,
H.
right, sorry. Yeah, this is G times. Just G times. Yeah, sorry. Yeah, definitely. Okay, so then so this makes this G times H into a homogeneous vector bundle over the homogeneous space G quotient H. Right. Then we can define the induction functor in the GH of M to be the global section of this homogeneous vector bundle. So an algebraic interpretation of the above construction is as follows. So we first consider the G times M module structure on M tensor f of G. So namely, we let GH acts on M tensor F to be HM tensor LG RH for G and G and H left and right regular representations. Okay. So even more concretely, this means the induction from H to G of M is M tensor with F of G, and we take the H invariant. So these are precisely functions from G to M such that FGH equals to H inverse of F of G with any H in H and G in G. Okay. So we have this Frobenius reciprocity. For any H and the HG, we have G of N and the induction from H to G of M. This is a symmetric to a whole between H modules restriction from G to H of N and so now let's look at the few Vowel modules and the Vowel modules.
Can I ask a question or make a comment?
Yeah, sure, please.
Maybe just if you're coming from the world of finite groups, or maybe from other parts of representation theory, maybe this induction might also be called co-induction. Like induction would be like tensoring with the group algebra, but co-induction is where you do it on functions. But for symmetric, if you're in the symmetric algebra setting, then these things become the same. But here, the natural thing to do is to work on functions.
Right. Yeah, thank you for the comment. Okay, let's look at Vowel modules and do Vowel modules. So for any dominant lambda, and we have this notation lambda star is minus W0. So recall that W0 is the longest element in the Vowel group. And we define the dual Vowel module lambda is the induction from B to G of minus lambda star. Okay. All right, let's look at an example. Let G equals to SL2. So in this case, the homogeneous space G quotient B can be identified with B1. And in this case, G times minus N, this is isomorphic to O of N. Then M of N, which is the global section of our line bundle, O of N is nothing but this I write as F X Y, and these are the degree in homogeneous polynomial. In X Y. Okay. Now the Vowel module is just defined as the dual of M in the star. This is okay. And then I should also mention there's an equivalent definition of Vowel module using distribution algebra. So so recall that in Ivan's talk, we see this distribution algebra, G of Z, sits in the universal envelope in algebra of GQ, and it has spaces pi of E alpha. Sorry, let me just start with minus alpha. E minus alpha of this divided power K alpha. Pi. Check beta, simple roots pi alpha E alpha, N alpha. So where K alpha, M beta, and N alpha are non-negative integers. Then we can define W lambda prime to be the distribution algebra quotient left ideal generated by, so E alpha and alpha. So, so beta check and beta minus check.
It's lambda.
Yeah, it's really lambda. Thanks. So, lambda beta check and beta, and E minus alpha of K alpha. So where okay, just write it this way. So and beta is greater than 0, and K alpha is greater than the pairing lambda. Oh. So we can see that in this way, this W lambda prime is finite dimensional. And in fact, this is equivalent to our previous definition by the following universal property of the Vowel module. So any finite dimensional representation G, we have G, lambda isomorphic to form up to B modules V, and this minus lambda star, and B whole between the Vowel module and V, this is isomorphic to form B of F lambda and B. Okay. So by using the part B of the lemma, we can verify that the W lambda prime, which is defined using the distribution algebra, agrees with our previous definition of Vowel module W lambda. And the proof of this lemma is not hard. So A is just a Frobenius reciprocity, and B is basically just Frobenius reciprocity plus duality. Okay.
Excuse me, I have a question.
Oh, yes, please.
Yeah, so when you define this while module, do you have a restriction on this lambda? Say, do you require to be dominant?
Right. I think I do require to be dominant.
Yeah. So can you go back to your definition, say in previous page?
Right.
Yeah. So do you mean m lambda star or m lambda? Yes,
Which
definition
part are you referring to?
So in the definition of w lambda.
I really mean lambda star.
Okay. And previously you defined m lambda for lambda.
Yeah, and previously I defined m lambda.
Okay. Okay.
Yeah.
Thanks.
Okay. Let lambda to be dominant. And this induced module is non-zero. Then the dimension of
This doesn't agree with your conventions, I think.
pardon me?
Doesn't agree with your conventions because this module was non-zero when lambda is anti-dominant.
Right. So how should I change it?
Well, you can say lambda minus lambda plus.
Right. Okay.
But it will be better to just maybe write m lambda.
Right.
Instead of this induced module.
Mm-hmm. Right. And okay. Yeah. Right, or B corresponds to a negative base. Yes.
No. Let's try to get to a right statement. So let's say that you write that lambda is in lambda plus.
Mm-hmm. Lambda plus, and I should probably say minus.
No.
No.
No. Just write m lambda instead of this int bg whatever.
Okay. So.
And by the way, we know that m lambda is different from 0. And one way how we know this is by looking at this w prime lambda, which you can see is non-zero for dominant weights.
Mm-hmm.
And this is for usual highest weight. So you can define Verma module over the distribution algebra, and then for every weight, it will have a unique simple quotient. And then you can show that for, well, I mean, you separately know that w prime lambda is a quotient of a Verma module, and so you know it's non-zero. So w lambda is a non-zero quotient. You can see this.
Mm-hmm. Right.
So we can remove m lambda different from 0.
Right. Then we know the dimension of the U invariant subspace of m lambda equals 1, and in fact, this space is F1. So let me just give a very quick sketch of proof. So m lambda is f of minus lambda star. And so it's G. So this tells us that the U invariant parts are those functions
And maybe let's keep the proof for the following reason. If you look at w lambda prime, then the corresponding property is more or less manifest.
Mm-hmm.
So you easily see that coinvariance of u in w lambda prime
Mm-hmm.
well, coinvariance of U minus in W lambda prime is one-dimensional, and it's the highest weight space.
Okay.
So maybe we could just leave the proof as an exercise.
Yeah, sure. I just leave it as an exercise. But let me just write down what you said just now. So we use this W lambda prime, this definition. Oops. We use this definition and we look at this part, and it's not hard to see that this is one-dimensional. And
Nope. It's coinvariance for U minus.
it's going, yeah, so for units.
Co-invariance.
Yeah, so that should be like, I think the coinvariance is like the coherence. Coherence. Look at and details. Okay. So as a corollary, the dimension of this home space between the vowel module and this and the view vowel module is delta. This is really an immediate consequence of the previous final. So the theorem tells us that for any dominant lambda, there exists a simple representation, which we denote by L lambda. It has a highest weight lambda, and moreover, L lambda is this unique irreducible submodule of the vowel module and lambda, and the unique quotient of the vowel module bracket. So the proof is more or less like the BGG categorical case. So we just look at the circle of this M lambda. This is simple. And second step, we just let of lambda to be this circle G of M lambda. And we can check our lambda U. The invariant part is the lambda space. And this dimension is 1. And finally, the existence just follows from Frobenius reciprocity, and the uniqueness follows from that too. So again, details are left as exercise.
Existence of what?
So the existence of such simple modules.
Well,
So-
I mean, every object of finite length has socle.
Yes. I should probably
So socle always exists.
always exists. I should
abelian and
probably remove the Frobenius reciprocity command. Maybe just
So you
existing.
need to know that the circle is simple.
Yeah.
But this sort of not very difficult.
Yeah. Okay. So the next topic that we are going to see is the Steinberg's tensor product theorem. So we first recall some results about the Frobenius morphism. So recall we defined this FRG of 1 from G to the first Frobenius twist of G. And we know that if G is defined over FP, then in fact G is isomorphic to its first Frobenius twist. So we compose such an isomorphism is for G1, we got a Frobenius endomorphism. There is a property about this. So first of all, let's assume B be an irreducible G1 module. Then the pullback of V along to G1 is also irreducible. And if we pull back to this simple module L lambda along this Frobenius endomorphism, we get L P lambda. So the proof is clear by the following two observations. So first of all, FRG1 is an ipmorphism. And the Frobenius endomorphism restricts to the rising to power p at t. So let's look at the main theorem of this section. So before stating the main theorem, let us make an assumption. So we'll assume G to be semi-simple and simply connected. So this assumption is actually harmless for the following reason. So because any reductive group G admits a surjective central isogeny from T plus G prime. So here, T is the connected component, this neutral component of Z of G, and G prime is semi-simple and simply connected. So we let lambda 1 plus to be the following set of weights, where lambda is dominant and lambda pair wave of I check is less than P for I. 1, 2. So the elements in this set are called the P-restricted. Now, by our assumption of the semi-simplicity and the simply connectedness of G, so lambda can be written as the sum of G to the power of I, from 0 to n, where all these lambda i's are P-restricted.
Right. There is echo, and turning off the microphone, I'm not sure. Let's try to address this issue during the break.
Sorry, pardon me. What is the, oops.
You have echo.
I have echo.
You do. And let's address this during the break. It's not particularly bad, but let's address this during the break.
Okay,
Which
sure.
in particular means not now.
Well, let me see how to resolve this echo.
Let's do this during the break, Jize.
It is good because it means that everything will be repeated twice.
Yeah, sure. Let's resume over.
Well, we already have things repeated twice and more than twice, but let's resume. Let's address this during the break.
Yeah, sure.
And this wasn't an echo; it was me repeating things. Jize.
Yep.
Please continue your lecture.
Yeah, sure. Okay. Okay. So we have L lambda is isomorphic to L lambda 0. Tensor is for G1 star of L lambda 1. Tensor da 2 for G1. Star R times of L. Okay. And here's also the second statement, which is going to be very useful in proving the first statement. That is, so we recall the Frobenius kernel of G1 in G, which is just a kernel of this Frobenius morphism. And sorry, it's the first Frobenius kernel. Then the restriction of L lambda to the Frobenius kernel is irreducible. So before
You mean
proving
L lambda I.
sure, then yeah. So before looking at the proof of this general theorem, let's take a look at the SL2 case. So let I be 0, 1, dot, 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 to p minus 1, and M be an irreducible G model. Then Li tensor with the Frobenius twist of this M is irreducible. Let me give some ideas of the proof. So the reducible G modules L0, L1 to L p minus 1 are also irreducible when viewed as Lie algebra modules. And we know from Ivan's talk, this is equivalent to irreducible G1 modules. Okay. So every irreducible G submodule of oops, of Li tensor with this for G twist and takes a form Li tensor M0. So where M0 sits inside for G1 star. Okay. Then we know that M0 is in fact irreducible G1 module. And this is yes. Is irreducible.
Something's wrong. So you want to say that M0 is a G1 submodule in M.
Right.
That's not what's written.
Aha, should be. So okay.
Well, I mean, whether or not it's irreducible is not important. It's important
But
that
it's
it's a submodule.
It's a submodule. It's really a submodule. Yeah. So an immediate corollary of this lemma is the following. So for I is 0, 1, 2, 2p minus 1, and j be a non-negative integer, we have an isomorphism between L I plus pj. Isomorphic to L I is for G star L. And for any dominant lambda, L lambda admits decomposition. So where lambda equals to the sum of p to the power of I, lambda I, I see in the previous section. Okay.
All right, maybe it's a good time for a break. And before we go for a break, are there any questions?
Well, does this tensor product theorem tells us anything about L lambda when characteristic is 0? It might be a vague question. Does that make sense?
So you do see something like this in characteristic 0 in the following weird way. So suppose I have, let's say, a finite field extension of Q, and I want to know what, let's call it, I don't know, F for some field, and I want to know what the finite dimensional irreducible representations of GLN-FQ are, GLN-F are, okay? So what you get a tensor product theorem, also due to Steinberg, so a Steinberg tensor product theorem, that the irreducible representations of GLN-F are tensor products of irreducible algebraic representations of the algebraic group, but pulled back along the different possible inclusions of your finite extension of Q into the complex numbers. So you have some Galois groups worth of ways of embedding your field into the complex numbers. And for each one of those, you can pull back algebraic representations, and then you tensor them together. And that gives you all the irreducibles. And so somehow, like in characteristic P, you have this weird fact that like the Frobenius is somehow like an element of the Galois group that's realized by something algebraic. So like we see this weird kind of Galois action happening just inside of algebraic representations, whereas in characteristic 0, it's somehow external. You have like this external action of the Galois group. So that's a partial answer of how you see this in characteristic 0.
Thanks.
Thanks for the comment. So we have seen the Steinberg's tensor product theorem in the case of G equals to SL2. And in order to deal with a general situation, an essential ingredient is to look at the representations of the first Frobenius kernel. So why is this? Because we have actually seen in the previous section that we relate this G module structure to the Lie algebra module structure, and then to the G1 module structure. So so the representations of G1 just naturally appears when we consider the SL2 case. Now, in this section, we will take a closer look at it. Okay. So we first look at these representations of T1. They are also completely reducible. And the irreducibles are parametrized by lambda quotient P. Okay. So the rough idea is really to write down the basis of the distribution algebra of G1. And
I'm confused. So you're talking about representations of T1.
yes,
Why would we write down basis for distribution algebra of G1 for this?
right. Probably. Okay. Yeah, I just want to say that because the triangular.
But it's representations of T1,
right.
of the torus part.
Right.
What does it have to do with triangular decomposition?
Sorry, I probably messed up something. And
well, we can just leave this as an exercise because, well, I mean, we know the algebra structure of distribution algebra of T1, and from there, the claim is pretty straightforward.
just yeah, just look at sorry, just messed up. Just look at the structure of the T1. And the details are left as an exercise. Okay. Now we consider this module. I'm one lambda and a W1 lambda. So these are defined in a very similar, exactly same similar manner as the usual dual vowel modules and vowel modules. Then we know that so M1 lambda is the B1 invariant part of FG1 tensor with F minus lambda star. So this will tells us that the dimension of M1 lambda is P times dimension of U equals to the dimension of W1. So
So P to the power dimension of U.
exactly, sorry, it's really to the power. So as a remark, we can actually define MR lambda and WR lambda. Then the dimension formula will be p to the power of r times the dimension of u equals to the dimension of the r's vowel. Okay. Now for any lambda sits inside the lambda quotient p lambda, there exists a unique simple L equal to L 1 lambda. So this is the unique sub-representation of M1 lambda and unique quotient of W1. So one example of this is, let's look at M1 of P minus 1 row.
It's unique simple. Yes.
Pardon me?
It's the unique simple sub and simple quotient. Yeah.
Yes, this is a unique simple, but it appears as a sub of the M1 lambda and also as a quotient of the W1 lambda.
Maybe it's a question about what's actually written.
Okay.
Unique what?
It's a unique sub-representation of M1 lambda and okay, it's the, how should I say? It's, yeah, which is a sub-representation of M1 lambda and a quotient of W1 lambda.
Well, it's unique simple sub and unique simple quotient.
Yeah, unique simple quotient, yes. And let's say unique simple quotient of W1 lambda. Okay.
Yeah,
So,
good, thanks.
So in the particular case, so this M1 of a P minus 1 row is in fact the same as W1 P minus 1 row, and this equals to L1 P minus 1 row. So this is in fact a Steinberg representation.
So, and maybe a couple of words about the argument. So you can consider G1T modules, modules over G1 which are graded. And then you can ask which, so they are simple subparameterized by weights. And then you ask which of these modules have a given Harish-Chandra character P minus 1 times rho. So we can talk about Harish-Chandra characters because these are modules over the Lie algebra. And when we look at this carefully enough, we see that when we forget the gradient, there is only one simple object. And from here, you can actually see that this object here is simple. So this unique simple object in the ungraded category is not going to have any self-extensions. So you see that M1 and W1 with this highest weight are self-extensions of L1, with this highest weight. And therefore, they're both simple.
Right. Okay. Can I continue?
Sure.
Right. So let's look at. Oops. Let's look at.
And maybe it's worth to point out that an analogous result holds for any R. There you will have a simple object with highest weight P R to -1.
Right.
And that you can, well, if you know the Steinberg tensor product theorem, then you can deduce it from the Steinberg tensor product theorem.
So more generally, so we have MR to R-1, right? So let's look at the proof of the main theorem in the general case. So it's basically done in 2 steps. So first of all, we prove the second statement, which says that so for any dominant lambda, the restriction of L lambda to the first Frobenius kernel is isomorphic to L1. Okay, so how do we show this? First of all, we look at this 5G from G to G. This is basically the conjugation by this element G. Then the twist of a G module L by this 5G is isomorphic to L itself for any simple G by module L. And element in G. Okay. And the second thing is, so if we are given a simple G1 module, so we can produce a projective representation of G on this map. And we need this Steinberg's result which tells us that for semi-simple and simply connected roots, so any projective representation in fact lives to a linear representation. And this is standard in characteristic 0.
So maybe a comment. So the way how we produce a projective representation structure on L is via those isomorphisms from the first bullet. We have an isomorphism corresponding to every G, but this isomorphism is only defined up to a scalar, after a non-zero scalar. That's why they may fail to give us an honest representation. They only give us a projective representation.
And finally, we can verify that highest weight of the representation coming from the previous bullet point is in fact lambda. Okay. So this basically is the idea of proving the second statement. And finally, we just need to prove, let me just write this as this. Second thing is we have L lambda plus P mu is isomorphic to L lambda tensor for G1 star of L. And the proof of this is similar to the SL2 case we have seen. Okay, all right, so this basically finishes our discussion on the Steinberg's tensor product theorem. So the next topic we will see is the Kemp's vanishing theorem. So here is a motivating question. So we have seen dual vowel modules and vowel modules, but how to compute their characters? So the answer to this is the following theorem. So let G be a connected reductive group. Then the characters of the dual vowel modules and vowel modules are the same as simple modules. With highest weight lambda in characteristic 0. So let's look at Kemp's theorem in this subsection. So, so first of all, we need the following result in proving Kemp's theorem.
Have you stated the theorem?
Yes, I will. I will state it very soon. Yeah. So, so let lambda be a dominant weight, and O lambda to be this line bundle on the homogeneous space G quotient B. Then the hierarchical homology vanishes.
Again, do you need F minus lambda or F minus lambda dual?
Right, you're right. Sorry. Yes. Yes. So this is O lambda, right? And right, and this is hierarchical homology vanishes for any I greater than 0. Okay. Right. The proof of this is roughly as follows. So first of all, again, we may assume that G is semi-simple and simply connected. And the second thing is, you notice a category of all rational representations of B have enough injectives. So this allows us to define the derived functor of the induction functor from D plus of rep B to D plus of rep G. And in fact, this induction functor from bounded derived category of rational representations of B to bounded derived category of rational representations of G. So I should mention that geometrically, so this derived functor is taking cohomology of homogeneous vector bundles.
Which makes sense when you start with a finite dimensional representation, strictly speaking.
Sorry, yes, I should really say. Yeah, for finite dimensional modules, yes. For homogeneous bundle, sorry, cohomology homogeneous vector bundles. For finite dimensional. Okay. And the third thing we need to prove this theorem is that for any lambda in lambda, so it's O lambda is ample if and only if it pairs with all the alpha check is greater than 0. And the ampleness tells us this is by one direction of the Sayre's cohomological criterion. That there exists some natural number R such that the cohomology of this O minus rho tensor with O of lambda plus rho twist P. Twist P to the power of R is 0 for any I greater than 0. And in fact, this left-hand side, this is nothing but Ri of this vector functor from B to G of F PR minus 1 rho tensor with the Frobenius twist of F minus lambda. And finally, we need a proposition. Tells us that for any R is greater than or equal to 1, and M, the finite dimensional P module, we have this induced module f minus p to the power of r minus 1 rho tensor is pullback m. This is isomorphic to L of p r minus 1 rho tensor this pullback of the induced module from B to G.
But it's no longer Frobenius for B. It's Frobenius for G.
For G, yes, sorry for the type. Yes, definitely for G. We have already induced. Yeah, the proof of this is kind of technical, but instead of giving all the details, let me just say we mainly make use of so the proof.
But maybe before you comment on the proof, let's try to see how we apply this. Why we need this result.
Yes, so because so as we see, okay. Right, because we have already seen this hierarchical homology of how should I say?
There is a function of a pointer, which you find on the panel above, where you have pen, erase, and so on. There is this thing with, you know, it's the rightmost thing in this panel. To the left of the red. So we have a red circle. Directly to the left, there is a pointer.
Okay, maybe. Maybe. Say. This is. Sorry. Okay, but maybe let me just say a few words. That's maybe let me just say it like real quickly. How should I say?
Jize, in your so can you use a pointer?
Let me try to find it.
My previous explanation was on the location of the pointer.
Yeah,
it's on the top panel to the left of a red circle. In your iPad, nope. That's not a pointer. Directly to the left of the red circle.
Of the right circle? I can't. Sorry, I don't see that.
Yes, this should be the pointer.
Okay, sorry. Right.
So we want to show that the thing called LHS, which is Ri in GB of a long expression, is equal to 0.
Right.
So here, wait a minute, sorry. We know that it's equal to 0.
This is by set.
And this thing, can you point to it?
Right.
This one, yes. So this thing here is a special case of the left-hand side in the top line of the next page. This one. Right, so we know that it's 0 for m equal f minus lambda. So we know that the right-hand side is 0. But the right-hand side being 0 means that r int gb of m is equal to 0. And this is what we need to prove.
Right.
So that's how this proposition is used.
Is used, yes.
Okay, maybe you can continue with.
Right.
What you're
Yeah.
talking
Thanks
about.
for explaining the idea of the idea of the proof, and
also the idea of how to find the pointer.
and also the idea of how to find the pointer. Yeah, sorry. This is literally the first time that I'm using an iPad. So yeah, sorry for this. Yeah, and right. So Evan has just explained the role played by this relatively technical proposition in the proof of the main theorem. So now I will briefly say something about how to prove this relatively technical proposition. So first, we basically use two things. The first thing is the transitivity of induction functors. I shouldn't use this label. I was thinking about this. And the next thing is, we know that because this function from B to GR of B, this is in fact an exact functor. Since GRB quotient B is alpha. Okay. So for the details of the proof, you may find in Ivan's notes or it's in Youngsen's book.
So maybe I can just say a couple of words of how this is used. So we want to induce from B to G.
Right.
And in order to do this, we first induce to GRB, which is a subgroup scheme in G, and then we induce up to G.
Right.
And let's look at the expression in the left-hand side. So what's going to happen with this expression when we induce from B to GRB? Well, to do this induction is the same thing essentially as induce from BR to GR.
Mm-hmm.
That's what happens.
Right.
And from the point of view of BR, this second factor is a trivial module, because it's Frobenius pooled by R's power of Frobenius. So this induction is not going to do anything to this factor. It's only going to induce the first factor. And when you induce the first factor, what you get is a Steinberg module. But the Steinberg module is already a module over G. So if you further induce to G, you can take it out of the induction. And then you very quickly arrive at the result that you want.
Right.
It's somehow the idea of the proof. Of course, there are some technicalities in realizing this idea.
Yeah. Okay. Thank you for the comment. And okay. So how does this the campus theorem tells us about the characters of M lambda and W lambda? So this is basically via the following two steps. So first one, we know that the characters of Vowel module equals to the characters which is 0 of lambda. And
which is
so,
M lambda.
Yeah, which is just M lambda, yes, exactly. So we recall we have.
So maybe I should say that this notation is due to myself. So W lambda is the Vowel module, and
Right.
then M lambda is dual. So what you do, you just reflect M along a horizontal axis. It's like W along horizontal axis.
Yeah, and I think in Yanson's book, the vowel modules is denoted by V of lambda. In Yanson's book. So right, so I should say recall that. So we have this. We have the Cartan evolution. Tau from G to G, such that tau square equals to 0, equals to identity, and tau restricted to the maximum torus is the identity of the torus, and it sends u of alpha to u of minus alpha for any alpha. But then the vowel module W lambda is isomorphic to this tau twist of M of. So the second ingredient is characters of M lambda equals to chi of F lambda.
I think you forgot dualization somewhere.
I forgot dualization.
Yes, because you cannot twist the while module with an automorphism and get a dual while module.
Right. Then I should.
So they have a different categorical structure.
Right. So let's see.
So it's really dual on one side, and it doesn't matter which one.
Okay, let me just say.
It's the previous line. You need to put a duality sign in the previous line.
Right, right. Okay.
Nope.
I think it's sorry. Start. It's a right. It's really sorry. This is right. And the second ingredient is the characters of this dual while module is the Euler characteristic. I will define it. So this is chi of F lambda is defined to be sum, the alternating sum of L lambda for I is greater than or equal to 0.
So what's going on with notation?
I'm just
So it's Euler character. It's cohomology of a line bundle on the Flag variety.
Yes, exactly.
Which is not something denoted by F lambda.
So, okay, so right, I've been messy about the notations.
Well, almost correct, but it was F of minus lambda dual.
Minus lambda star. Yeah, sorry, I always forgot about this. Yes. All right. Okay. So let's look at the extraction. And highest way module structure. Okay. So here's a proposition tells us that extra gi of w lambda and m of mu equals to 0 if I is greater than 0 for all lambda mu in lambda plus. Okay. All right. Again, let me just very briefly say how this is proved. So first of all, we can transfer this X group to HI of G of M minus W0 lambda tensor tensor M of mu. And the second thing is we know this is really this M minus W0 lambda tensor M of mu. This is really HI of G. Let me start this page. G of psi of B of H0 minus W0 lambda tensor F of mu, and it's also isomorphic to HI B of F minus W0 lambda tensor M of mu. Okay, so here we really use the tensor identity and campus vanishing theorem. So so now the left-hand side is non-zero. So if there exists some weight mu of M of minus W0 lambda and some weight mu prime of M of mu, such that first of all, this mu plus mu and minus W0 lambda plus mu prime are in this minus the greater than or equal to 0 span of phi plus. And secondly, so the weights of mu plus mu, the height of mu plus mu and minus W0 lambda plus mu prime are less than or equal to minus I. So here the height of sigma and alpha for this alpha in pi is just the summation of n alpha. So so again, to see this statement, we can just take an injective resolution of K. So there is an injective resolution of K, such that, so first of all, this A1 is the injective Hall of K. And for the rest, IJ has a following property. So all the weights all the weights are in phi plus, and heights are greater than or equal to J. So again, this is kind of this is a little bit of technical, and you can find the proof in Yanson's book. Okay.
Excuse me. So what is the second condition? The height of mu plus nu and height of...
the height of mu plus nu and the height of minus W0 lambda plus mu prime are less than or equal to minus I. So if you I. What is I? I is the degree of this cohomology. So if the I's cohomology is non-vanishing, so we know that the height must satisfy this numerical condition.
Okay, thanks.
Okay. All right. I think I'm already run a little bit of time. I will try to finish the last thing. So the final topic today is the linkage principle. Okay. Again, the motivating question is as follows. So which L lambda occurs with non-zero multiplicity in M lambda? And this is equivalent as in W of lambda, because they have the same characters, so they correspond to the same class in the, they correspond to the same K0 class. Right. So let me quickly recall. We know the answer to this question in the BGG category O. So if G is a complex some simple algebra, O is the BGG category O, and we have this Brouillard order. So on this weight lattice, so this is if, sorry, this is mu is less than or equal to lambda. If we can find a sequence lambda 0 equals to lambda and lambda 1 dot 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 lambda r equals to mu, such that lambda i plus 1 is less than lambda I, and lambda I plus 1 is the reflection of lambda I by some s beta I, where beta I is simple root. Is a simple root. Then in this case, if mu is less than or equal to lambda with respect to Brouillard order, then we know this is non-zero.
The other way around.
Sorry, this is right. So if this is multiplicity, sorry, if this multiplicity is non-zero, then mu is less than or equal to lambda. Okay, yeah, thank you for the corrections. So we first define this dual alpha and Vowel group. So this WA is defined to be the semi-direct product of the Vowel group with lambda R. So recall lambda R is the root lattice. And we define this P dilated dot action of this alpha Vowel group. So this is defined as follows. So for W inside W, it's just the usual dot action. Well, for mu in lambda R, then T mu is P of lambda defined to be lambda plus P times mu. Okay. So we also define A plus to be order lambda in lambda such that lambda plus 0 paired with alpha I check is greater than or equal to 0 for all I equals to 1 to dot to R, and lambda plus 0 alpha 0 check is greater than or equal to minus P. Okay. So I think I will just give a very quick example of the SL2 case. So in this case, we see that so let's say P equals to 5. So in this case, this is minus 6. So in this case, minus 11, and so minus 1 is translated to minus 11 by reflection to this hyperplane, minus 6. Well, 4 is translated to 14 via this translation with respect to the hyperplane 9. And in this case, the A plus is the region from minus 1 to 4. Right. And if time allows, I will write down some concrete formulas of this P dilated dot action in the case of SL2. And yeah, okay. So I should introduce this new order, which is similar to the Burha order. This is the linkage order. So we say that for lambda mu in lambda, we say lambda is upper arrow mu if we can find a sequence lambda equals to lambda 0 equals to mu, and then lambda 1 dot to lambda k equals to lambda. So lambda such sorry, and some often reflections. Is 0 to sk minus 1, such that lambda I is obtained by lambda I minus 1 via this often reflection. And we further assume that lambda I less than or equal to lambda I plus 1. So a quick remark is, so lambda upper arrow mu implies lambda is less than or equal to mu, and also mu is in the orbit of lambda with respect to the action of the alpha Vowel group. All right. Then okay. Just a theorem. If the multiplicity mu dot L lambda is non-zero, then we have lambda upper arrow. And a quick corollary of the theorem tells us that if the first X group, L lambda and L mu, is non-zero, then mu is in fact in the WA orbit of lambda. And for any C in A plus, so this block, right, the CG, is the stair span of all the L lambdas, where lambda is in this orbit of the C. Then we have this decomposition, rep G goes to C in A plus, rep C. So I think I just finished my talk, and I want to thank you for all the comments and the corrections and your attention. Thank you.
Okay, let's thank Jize for the talk. Are there any questions?
Can I ask how you deduce the corollary from the theorem?
Right. Let's see.
It's okay if you didn't prepare that. Okay, I don't see a very easy proof. So
right. I probably don't have like a quick answer to this question. Sorry.
Okay. Rafael, am I eligible to answer?
Yes. I mean, I don't see a one life deduction. So please, yes.
Well, if you know, you need to consider the relative order between L lambda and L mu, and if you see that they are not comparable, then you see that the extension splits just by considering, you know, homes from Vowel modules. And then you can assume that they're comparable, but by duality, you can actually swap the order.
So the first part of your argument, I mean, the x1 being non-zero doesn't mean that does not mean that they will be both contained in the same Vowel module. I mean, how do you see that?
So let's we need to consider three cases. So let's assume that lambda and mu are not comparable with respect to our order. Then let me consider homes from W lambda and W mu to this extension.
Yes.
So both of these homes are non-zero. For highest weight reasons.
Yes. Okay. So that's okay. That's a key point. Okay. I see that. Then you're good. Okay. I see. Yes. You use the universal, some sort of the universal property of Vowel modules wait. No. But yeah. That's, I suppose that's.
Well, and I use the usual order.
Yeah, with the usual order. Yes. So it's not an immediate corollary of the theorem. That's what I mean. I mean, you need
well, you need a bit of argument.
You need a bit of argument. Yeah, but I see. No, I see. Yes, it's not so bad. Yes, thank you.
And I think it's a kind of a general thing about highest weight categories.
That's what I was trying to think, but I can't see that. I can't see that.
All right, it's my honor and privilege to give you an exercise of highest weight categories.
Yes.
Because essentially what I know about highest weight categories I learned from your paper.
So you say, so this is true for general highest weight categories. That's what you're saying. Okay, I forgot that. Okay.
Right. So in a general highest weight category, if you have two labels which are not comparable, then there is no extension, and then you have this dichotomy between,
Yes.
you know, if between the order in two directions.
Yes, no, I understand. Yes, I know, I understand. Yes, thank you. So you have to do, you have to split. I mean, it's interesting what you bring that we didn't see too much, is that sometimes you have to look at, yeah, it's not like you get direct, you can reduce directly. It's not just one case. You have to look at different cases, and these three cases, as you say, not comparable, one less, one more, really, and analyze each situation. Yes, that's a good point. Thanks.
All right.